Hello everyone. We're going to discuss a final video on section 11.4. In this video, the learning objectives will be describe the effect of solute concentration on various solution properties. And here we're specifically looking at osmotic pressure. And then the final learning objective, explain the process of osmosis and describe how it is applied industrially and in nature. Okay, so let's go ahead and take a look at this. Um, this one is a little bit different than the other colligative properties because it's not related to a phase change. So I wanted to have a separate video about this. However, it is also a very important colligative property, especially for those of you going into any kind of a medical field or biological field. It also comes up in engineering fields sometimes. I can speak somewhat from my own experience related to membranes. We have something called selective permeation, and some materials are able to cause this selective permeation. What this means is that there is some characteristic of molecules or ions that allows some of them to cross a membrane, cross this this material, and others will not. We refer to these things as semi-permeable membranes. They could be natural, they could be something that is industrially produced. But they are very useful in a lot of regards. So a semi-permeable membrane allows selective permeation of some ions or molecules related to others. We're showing an example of that down here. So we have this container, so it's kind of a U-shaped tube, and on one side of this we have only a solvent. On the other side we have a solution that has a solvent as well as some other solute. Separating these two is a semi-permeable membrane, so some substance that allows one thing to cross but not the other. Oftentimes it is the solvent that can cross the membrane and the solute that cannot cross the membrane. So it will depend on what you have in terms of which thing can cross the membrane or not. So the membrane will have a property of selecting one versus the other. So what's going to happen here is we have this dynamic equilibrium where we have the solvent will be going back and forth across this membrane because it can. Meanwhile, the solute will not. The solute is not allowed to cross this membrane. We're showing here the solute as being larger than the solvent. In some cases, it's based on a size. In some cases, it's based on some other properties such as, polarity, for example. Whatever the case, what will end up happening, and we're not going to get into that level of detail here in terms of why, but what ends up happening is the solvent can cross over here, and the solute cannot. And over time, you'll end up with this side will have a higher elevation, and because of this, we have a pressure called the osmotic pressure that will form. And what's happening here is the solvent can go back and forth, back and forth, back and forth, but it essentially would prefer to be, we kind of ascribe some, characteristics here to the solvent that it probably doesn't actually have a preference. But what we end up seeing is that it ends up wanting to essentially try to equalize these concentrations. That's what it tries to do. So because this one is more concentrated, we add more to it. We add more solvent to this side to try to dilute it down a little bit. And you're never going to get it, in this case, never will be exactly the same because this one is pure, so we can't dilute something down to being a pure solvent. But it will keep going until we reach something called the osmotic pressure. So this is called osmosis, and let me go ahead and highlight this. It's a diffusion-driven transfer of solvent molecules through a semi-permeable membrane, and we call that process osmosis. The details of the process itself, there's a lot we're not getting into here, but what you want to understand is that we're moving towards trying to make them equal in this process, and we're not going to get there, but we'll end up by diluting the more concentrated solution and lowering the amount of the pure solvent. And we have this osmotic pressure we need to talk about a little bit. So the osmotic, so again, you're never going to get this one to be the same. So it's going to keep going, and it doesn't go forever, right? We don't completely dry this out. The stopping point is based on something called the osmotic pressure. So the osmotic pressure is the pressure at which osmosis will stop. And this is how we can calculate what that will be. We have the molarity of the solution. We can use molarity here because we're not doing anything that involves a change in temperature. So molarity times gas constant times absolute temperature. And that gives us the osmotic pressure. We can use this in some cases to maybe find the, find the molar mass of that solution, and we might see an example of that in a bit. We're more here again, though, focused on the qualitative idea, qualitative aspect in terms of understanding the concept. So here we're showing some calculations. Again, the focus won't be too much on the calculations for this idea, more so on the concepts. So let's look at another example. So we know that osmosis will stop when we have osmotic pressure. What if we have a pressure greater than that? So somehow we have this the solution that has some solute in it, and we press on it, and we have a greater than osmotic pressure. What's going to happen is the net flow is going to be of the solvent across this semi-permeable membrane, and we end up getting more pure solvent than we did to start with. This is sometimes called reverse osmosis. You may have heard of reverse osmosis or RO as a process that can be used for purifying water. It is the process that we use to get our DI water. And so the idea here is that you can apply a force, use a membrane, and purify water in a way that uses the semi-permeable membrane along with the pressure. This is also often used in other water purification systems, a method similar to this. It doesn't have to involve a U-shaped tube. Okay, so that's not always going to be there. That's more for the point of illustrating it for us. Okay, so there's some more discussion here about that reverse osmosis process for water purification. Okay, this is also a process that takes place in our bodies. So in our bodies, we have semi-permeable membranes in some of our cells. One of those cells would be a red blood cell, and it's one that's important due to some medical applications. If we were to put a fluid into the bloodstream, one thing we would need to be aware of is osmosis and how that would relate to the red blood cells. So water can cross a red blood cell. Other things can't. So Things like salt cannot cross that membrane. And our red blood cells have a certain concentration inside of them, a certain salt concentration. And it's not just salt, but other things, some sugars. There's a variety of things. And we can measure what that osmotic pressure is inside the red blood cell. And apparently this is what that is. You don't have to remember this number. But the idea here is that if you have another liquid next to that red blood cell, you're going to have that exchange of water across the membrane. And you want to be careful that that doesn't cause damage to the red blood cell. In order to do that, what we need is something called an isotonic solution. And let me go ahead and highlight that. Which means that they need to have the same osmotic pressure. So any solution that is put into the body through an injection should be isotonic, and that means it has the same concentrations of what is in the red blood cell. It doesn't have to be exactly the same species, but essentially the same osmotic pressure. If it doesn't, we can have problems. So here we're showing an example where we have more water going in to the red blood cell than is coming out. So what's happening here is maybe we have pure water. Maybe we just didn't have anything dissolved in the water that was injected. And so what's happening is where the water is trying to dilute the inside of the red blood cell. So all this water keeps flowing into the red blood cell, and it will eventually burst. And that's a problem. We would not want that to happen. So that is called a hypotonic solution. So it's less concentrated. So we're assuming maybe a pure water, and it causes a problem. You could have the opposite problem. Let's say you have a very salty solution that is injected into the body. In that case, you're trying to dilute that solution down by pulling water out of the red blood cell. So that's called a hypertonic solution. What happens there is that then the red blood cells are going to shrivel up, and that is bad. So what you really want is you want exactly the same concentration. So an isotonic solution, both inside the blood cell and outside, so of the same osmotic pressure. Okay, so that would be what would be helpful there. Another similar application to this idea, not exactly the same, but similar, is why we don't drink seawater. So what would happen if you drink seawater is that you have a higher concentration of salt in the seawater than you do in your body, and you would have a similar process of water coming out of your body into where that seawater is. So if it's in your stomach, water is coming out of the surrounding tissue into your stomach, and now you have a bunch of water in your digestive system, which is what leads to people getting sick. So that's why we don't drink seawater. It's a similar idea to why we use isotonic solutions when we inject people. So some applications there to the healthcare field. So you want to be aware of, again, we're not doing calculations, but aware qualitatively of the direction of change that would happen based on the relative amounts of solutes from one side to the other of a semi-permeable membrane. So we can also use this to find the molar mass, as I mentioned earlier. Again, potentially homework question related to this, but it will not be a focus of the exam. So a couple examples there of that. So that is it for section 11.4, and actually then for module 11. So please look at the worksheets, do the homework, take the quiz, and let me know if you have any questions.